So we have this basic understanding that if I happen to swim in, say, a pond or anything, to be honest, if we happen to swim over there, as and when we dive deep, right, what happens? The force exerted by the water, it increases. So we'll feel more pressure. And in some cases, our eardrums and head and all of that starts paining. Now, I have 4 containers over here. So my question to you guys is, see, this height is same. I'm going to take up different points, say A and B, and say P and Q, and so on and so forth, right? In this case, V and W. So my question to you guys is, in which case the pressure difference will be more? Remember, the height is same. So PB minus PA. The pressure difference, I want you guys to compare it with PQ and, let me write it, PQ minus PP and PW minus PV. Yeah. Which of the 3 will have the highest pressure difference? Highest value, like 20. Yeah, I think you guys understood. Which will have the highest difference? Actually, the pressure difference in all of the 3 cases will be the same. But yeah, obvious point would be the container 1 has more water than 2 and 3 and 4. So why is it same? We'll understand that. But point here is, all the 3 cases, since we have the same liquid at the same gravitational height as well above a particular surface, the difference between the 2 points in each of the container, since the height is the same, h is same in all the 3 cases, right? H is same, all the 4 cases actually. The pressure difference will be same. The pressure difference in all the 4 cases will be same, even though the structure is weird over here. Here it is slanted, here it is L-shaped, but the pressure will be the same. Okay, so this is given a special name, and this is your hydrostatic paradox. Hydro is to do with your fluid, static is stationary. Paradox is that this weird scenario we are looking at. If we ask a small kid, intuitively we'll tell that because the container 1 has more water in it, the pressure will be more over here. But it's not the case. Pressure is same for all the 4 cases. And this is called as hydrostatic paradox. The basic idea is that the pressure at a point in a fluid at rest depends on the depth of that point, but not on the size or the shape of the container. The size and the shape will not matter. Okay, so the actual statement is that the pressure exerted by a static fluid at any given point depends solely on the depth or the height of the fluid column above that point. The density of the fluid and the gravity, of course, depth, density and gravity. Basically, I told it's the same liquid above the surface of the earth. But yeah, density and gravity matters. So remember, in all of these cases, we are using the same fluid. Okay, they are next to each other. So this is just above the surface of the earth, or anywhere actually, but they are next to each other. So G is same for all. G is same plus G is same. They are exposed to the same gravitational pull. If all of this is satisfied, then for a fixed height, the pressure difference will be same. Okay, guys. So not on the shape, volume or total mass of the fluid in the container. The pressure is not dependent on the shape or volume or total mass of the fluid in the container. So clearly the shapes are different. The amount of water is different in each of this case. But because of this set of conditions, they have the same pressure. Okay guys, so basically if this is a pond per se, and if I change the shape of this pond, if I make it this, even now I will continue to experience the same amount of pressure on me as when I swim. It won't matter that the shape is different now. The amount of pressure that I'll experience while swimming in this way will be the same. Okay? But why is what we are trying to understand. For that, I'm taking up three cases, sorry. One, this is two, and this is three. So you can see the third case, we have a wide base, and I'll consider point A and point B over here. Okay, so let me actually count it. 1, 2, 3, 4. Okay, let's take point. The difference is 4 because we need to keep the height same, na? So that's point B and so on and so forth. So we have 1, 2, 3. Oh, we just have 3 over here. This is 4, right? No, this is 3. Difference is 3. So this is 1, 2, and 3. This is point A and say this is point B. And 1, 2, 3, point A and point B. It can be anywhere actually. I'm just taking random set of points. Now, starting with case of narrow vessel. Okay. Now, so it has to do with side walls. In all of these cases, the side walls play a role. Here, the side wall is clearly vertical. These are vertical. They're up straight. So, what happens? What does the water do? Water exerts a horizontal push, and the reaction force will be horizontal. So, here, water or any fluid, it pushes horizontally on every wall element. Okay. So why it matters, I'll explain. So the reaction force will also be horizontal. So there is no vertical component. So let me make a small note. The vertical force from walls will be 0. Okay. So why is this an important point? I'll explain it over here. Now we have case 2. So we have a narrow base with a wide mouth. So clearly the water here is more than case A and C actually. So if you would ask me if when I was a kid, I would have told, yeah, this will here in this case the pressure will be more, but it's not the case. Even though the water is more over here, let's look at the side wall. The side wall slope is this manner, and we know that the force exerted by the fluid will be here in this manner. Say water in this case. As a reaction, the wall will exert a force in this manner. Okay, let me take that. So in this direction, right? So now if I resolve this vector, we have a force in this direction and in this direction. So there is an upward reaction by the walls, right? So this upward reaction from the wall, let me write it off. Upward reaction from the wall cancels the weight, again, all this is a very simple set of explanation, but yeah, somewhere we are starting off. Weight of the extra water above. Okay, so it cancels out the extra water above. So because of the upward reaction, so basically there's some component which is pushing them up. So what happens, even though there is excess of water, the side walls kind of cancels the extra force that might be exerted by the water present in this container. It will be cancelled out. So as a net downward bottom force will be dependent on only the narrow section. So basically only this part will contribute to the, so you can see that it looks like a case A scenario, right? Only this part will be contributing to the downward push. Okay, so this only the narrow vertical column directly above the bottom, it pushes things down. And that is the only contribution. So basically the side wall, it holds the extra water. They cancel the downward push, and only the narrow column contributes. Okay, yes. So from here we can infer that only narrow column contributes. Okay, then moving on to case C. So what do we have? Here we have, remember, a fluid will push at a given point, will push equally in all the directions. So it will push the surface with an equal amount of force outward. As a reaction, the container will push the water inward in this direction with the same amount of force. So if I take up that and if I resolve this, what we are looking at is this scenario. So here the wall pushes down on the water. So this will push down. You guys agree? Remember, at a given height, the pressure is same. So as and when we go down and down, the column of water might reduce at say at B. There is a very small column of water, but this point, right, just above it, will have a huge pressure exerting on it. So the amount of force over here will be much greater than over here. So the reaction force will be much greater. Does it make sense? So here it will be not so much. Here it will increase as and when you go down, it keeps increasing. So as a result, what happens? The wall pushes down on the water. This adds extra downward force. The wall pushes downward on the water. Again, any fluid, it need not be water. This adds extra downward force. So basically you take up any point. So yeah, you might tell that, you know what, here it's not a big deal, you know, we have the same scenario. So this is okay, right? This region is okay, we can explain it. It's similar to case A, right? All of this is similar to case A. What about this region? You know, this is a question mark. This can be explained with wall. Okay, so at any given point, the water will push the surface perpendicular to the surface. As a result, there is a downward push, and when we resolve it, we'll end up with that extra bit of force that we need that will add up, and at any given point we have the same pressure, and so all of this will have the same pressure. Okay, so all in all, the wall pushes down to make up the missing water. Okay, so I can summarize it in this manner. Walls. See, all of this has to be understood. It's tough to explain, put it in words. Maybe not that tough, but yeah, it's easily understandable than writing it, at least for me. Making up the missing water, and so that's why we have the pressure to be uniform. Okay, so this is a very simple set of explanation. I think I started off over here. So what we are looking at is a paradox, a weird scenario. A scenario wherein if you make up a YouTube short or questionnaire or whatever that is in different platforms, and if I ask people will choose that in scenario A or in container 1, in this case, the pressure will be more at point B, right? I'm sure most will choose that, but it's not the case. The pressure is equal in all the cases, even though the water or any fluid happens to be the same in all of them. But why is that? Well, we can understand that with 3 different cases in narrow vessel case. So here now we can see that the side wall will not contribute anything. So the pressure is purely because of whatever is water above the base. But when it comes to wider mouth, water is more. So that excess water is handled by the walls. And in this case, I have not written it. The water is less clearly. Okay, actually it depends how wide the mouth is. The water might be less. Right? So even though there is less water, what is happening? There are positions in the container which is at the same height or same depth in this case. Just below A, say I'll call this as B dash. So the depth is same for B and B dash, B double dash. They are at the same depth. But the pressure turns out to be the same because again of the wall, because of the walls. Right? If you use our basic understanding of how water exerts force, right? We have done that. We'll be able to explain this. Okay, so you guys can, yeah, write what you feel makes sense. Again, write things which make sense. Don't write everything that I write or I show. Whatever makes you recall a particular concept, you should write that, a running note. Good exam notes are out there. We have books, printed books, and your school teachers also, college teachers also will be making you guys make notes. So don't make notes wherein you can write it for your exam. Make notes which helps you recall the concepts.